Symmetries play an important role in physics through Noether's theorem, but not only. We saw, for instance, that the Lagrangian has to be built as a Lorentz scalar in order to have Lorentz invariance of the underlying physics. We will now focus on gauge invariance, and in particular on local gauge invariance, and we will see how much it constrains the possibilities for the Lagrangians. But first, let's revisit the case of global gauge invariance for a free fermion obeying the Dirac Lagrangian. The Dirac Lagrangian depends both on psi and psi bar, therefore we need to specify how the global gauge transformation acts on psi bar as well. We can now look at how the Dirac Lagrangian transforms. Alpha being a constant, the covariant derivative has no effect on the exponential term, and therefore we can move it to the left and cancel it with exponential minus I alpha. As a result, a global gauge invariance is a symmetry of the Dirac Lagrangian. In the language of group theory, it's called a U1 symmetry. That's because the transformation is unitary, therefore we have a U for unitary. And it's also represented by 1 matrices, because exponential I alpha is just a number. And that's why we have 1, because it's a 1 matrix. So that's a very simple transformation, and therefore a very simple symmetry, which is usually obvious and here for any system. However, this is true for the case of global gauge transformation, where alpha is a constant. We are now looking at the case of local gauge transformation, where alpha is a function of space-time.